The Wolff-Kishner reduction is a very useful method for deoxygenating aldehydes and ketones. A hydrazone is formed, which then reacts with potassium hydroxide and water at high temperature to produce, through a stepwise mechanism, the alkyl product. The mechanism is essentially a series of proton transfers and loss of molecular nitrogen that results in the oxygen of the starting carbonyl being replaced by two hydrogens. The required hydrazone is formed through the reaction of an aldehyde or a ketone with hydrazine, in the same way that imines are formed. When the hydrazone is treated with hydroxide, a deprotonation occurs at nitrogen to give the conjugate base. The enhanced acidity of the NH bond is due to the presence of the electron withdrawing imine group, which also allows for delocalization of the negative charge in the conjugate base. Since water is the solvent, the conjugate base may be protonated at carbon to give a neutral azo compound. The azo structure is then deprotonated at nitrogen again, the enhanced acidity of the proton being due to the sp2 hybridization of the azo nitrogen. In the key event, a molecule of nitrogen is lost as an excellent leaving group to produce a very unstable carbanion. The loss of the gas is irreversible. Since the highly reactive carbanion is generated in an aqueous environment, it will be deprotonated quickly to give the final product of reduction. The Wolff-Kishner reaction is therefore a useful procedure for reducing a carbonyl in an aldehyde or a ketone to a methylene group. The reaction is run under highly basic conditions, so it is not compatible with other base-sensitive functional groups.